Okay, let's investigate this question. Given that f from x to y and g from y to z are such that g composed with f, I think I should have a little bit more here. G composed with f is 1 to 1. Are either f or g 1 to 1? You know, I've got to start hiring better proofreaders. That's all there is to it. Well, I'll tell you what. Maybe one of the best ways to do this is just to draw a simple picture or two where f composed with g, or rather g composed with f, is 1 to 1. And see if we can do anything to sabotage our function so that g composed with f remains 1 to 1, but either f or g, or maybe both, fail to be 1 to 1. So let's draw a simple picture showing g composed with f being 1 to 1. And let's play around with that picture. So here's f, here's g, and here's g composed with f. There. A very simple function. And notice that g composed with f is 1 to 1. We have two distinct elements in set X that are assigned two distinct elements in set Z. No two elements in set X are assigned to the same element in set Z by the function g composed with f. So g composed with f is 1 to 1. And so, for that matter, our functions f and g. No two elements in set X get assigned the same element in set Y by the function f. So f is 1 to 1. No two elements in set Z are assigned the same element from set Y. I'm sorry. I hope I said that right to begin with. No two elements in set Y are assigned the same element in set Z by the function g. So g is 1 to 1. No two elements in set X are assigned the same element in set Y. So f is 1 to 1. We have distinct elements in set X being assigned to distinct elements in set Y. F is 1 to 1. Two distinct elements in set Y being assigned to two distinct elements in set Z. G is 1 to 1. So g composed with f is 1 to 1. And the way we've drawn the picture, f is 1 to 1 and g is 1 to 1. But do they have to be that way? Let's just play around with this picture a little bit and see if we can preserve g composed with f being 1 to 1 while making either f or g not 1 to 1. For example, maybe we can do something in set Y like this. Now I don't want g to be 1 to 1, so I have to take this element 3 and assign to it an element that's already assigned to some other element in set Y. So I'll go like this. I have two elements in set Y that are assigned the same element in set Z. So G is no longer 1 to 1. But what about G composed with F? Is G composed with F 1 to 1? Let's see. I have two distinct elements in set X, and they're assigned two distinct elements in set Z. The two elements in set X are not assigned the same element in set Z, so F is 1 to 1. G is not. Now, can I do anything maybe to make F not 1 to 1 while preserving G composed with F being 1 to 1? I'll try doing the same kind of thing in set X. I'll put an element here. And in order for F not to be 1 to 1, I'm going to have to assign to C some element in set Y that's already assigned to another element in set X. I'll do something like this. And now elements B and C are assigned the same element from set Y by the function F. F is not 1 to 1. Now, have I preserved the 1 to 1-ness of G composed with F? Well, let's see. This element beta in set Z is assigned to both elements B and C of set X by the function G composed with F. Ooh, by putting this element in set X and assigning it the element Z from Y, the element 2 from Y, not only did I make F not 1 to 1, I made the composition of G and F not 1 to 1. So that didn't work. Let me put it back the way I had it. I did succeed in keeping G composed with F 1 to 1 while making G not 1 to 1. I couldn't do the same thing with the function F. And that may be an indication that if G composed with F is 1 to 1, then F has to be 1 to 1. Maybe the reason I couldn't keep G composed with F 1 to 1 and make F not 1 to 1 is because that's not possible. That seems to be what my picture is telling me. But I did learn something. It is possible to have the composition of two functions be 1 to 1, and at least one of the functions does not have to be 1 to 1. So let me write that down. So if we have the composition of functions 1 to 1, it turns out that this function doesn't have to be 1 to 1. But it looks like this one does, and that's what we're going to prove in just a second. Okay, here's what we're going to prove. If function f from x to y and function g from y to z are such that the composition g composed with f from x to z is 1 to 1, then f must be 1 to 1. And I will highlight my hypothesis here. there's my hypothesis. So I'll start out and say, let the hypothesis be given. And I won't write them out here, they're too lengthy. But I'm going to prove that f is 1 to 1. And I do that the traditional way. I'll pick f of x1 and f of x2 and y, and show that that implies that x1 equals x2 and x. Now, what I'd like to do is go backward from y to x. I have f of x1 and I have f of x1 and f of x2 here in y, and they're equal. And I want to backtrack here to set x and show that x1 equals x2. But there's nothing that will allow me to do that. I do have a hypothesis that says that g composed with f from x to z is 1 to 1. And I have to use that somehow. So I'm going to do something that seems strange, because instead of going from y to x, taking f of x1 and f of x2 and going backward to x, I'm going to take x1 and x2, f of x1 and f of x2 and set y, and go forward to set g, where I have g of f of x1 equals g of f of x2. It seems like I'm going in the wrong direction, but I think here that's what I need to do. I have f of x1 equals f of x2, and that tells me that g of f of x1 is equal to g of f of x2. Now, what gives me the right to say that? What special property does g have that allows me to say that? And other than g being a function, it doesn't have to have any special property, because f of x1 and f of x2 are equal, which means I'm plugging the same value into the function g on each side of the equation. Think of f of x1 being a number and f of x2 being a number. If they're equal, they're the same number, which means I'm plugging the same number into the function g. So I'm going to get something that's equal. Now, let me just change my notation in the next step. I'll write this as g composed with f of x of 1 equals g composed with f of x of 2. And now I can use my hypothesis, because my hypothesis says that g composed with f is 1 to 1, which means that if g composed with f of x1 equals g composed with f of x2, x1 equals x2. Technically, I'm done with my proof right here. But for the sake of any who might have been on autopilot while they were watching me do this proof, I'm going to extend them the courtesy of telling them what it is that I just showed. Here's where I started. I started with f of x1 equals f of x2. And here's where I ended up. x1 equals x2. f of x1 equals f of x2 implies x1 equals x2. That means that f is 1 to 1. And my proof is done. Now I have an idea. Why don't I do the same thing that I just did with f and g, but instead of doing it with one-to-one functions, why don't I do it with onto functions? And it may seem like we're playing games here, drawing pictures and so forth. And maybe in a sense we are. We are drawing pictures, and I hope we're enjoying this. I'm enjoying it. But just because we're doing something enjoyable and drawing some simple pictures doesn't mean that what we're doing is trivial. A lot of major revelations come from some very simple pictures, and we're seeing some right now. So we're going to do the analog of what we just did with one-to-one functions. We're going to do it with onto functions. Here we go. Given functions f and g such that their composition is onto, is either f or g necessarily onto? And the answer is, I don't know. Let's find out. Let's draw a picture of a couple of functions, f and g, simple functions, such that the composition is onto, and see if somehow we can sort of corrupt that diagram so that one or maybe both of the functions is not onto, but the composition is onto. So let's take function f from x to y and g from y to z, and then we have the composition g composed with f, and we'll try to make it a simple example, not so simple that it turns out that f and g have to be onto just because we made the diagram so simple or the example so simple. Simple enough so that we don't get lost in the details, but not so simple that we fail to do what we set out to do. This is looking a lot like the last one that we did. And every element in set Z is assigned an element in set X by the composition. Alpha is assigned the element A, beta is assigned the element B. So G composed with F is onto. G is onto, alpha is assigned to the element 1, beta is assigned to the element 2, and F is onto. 1 is assigned to the element A, 2 is assigned to the element B. So the composition of functions is onto, and the way we have it drawn, both F and G are onto. But is that the way it has to be? Let's see again if we can sort of corrupt things so that either F or G fails to be onto, but their composition is still onto. And I think I'll put an element here in set Y and send that to beta. Function G is still onto. And let's see, is G composed with F onto? Alpha is assigned to A, beta is assigned to B. G composed with F is still onto. Okay, here's what we've done. F is not onto. Given this element 3 in set Y, 3 is not assigned to any element in set X. So F is not onto. Now, could we do something similar to make G not be onto? I guess so. There, G is not onto. Now I guess the question is our function F, our function G composed with F still onto? Is there an element in set X such that gamma here gets assigned to that element in set X? Actually, no. Gamma, whoops. Yeah, gamma is not assigned to any element in set X by the function. So by making G fail to be onto, it looks like that caused G composed with F to fail to be onto also. You know, I'm not sure I can draw a picture of functions F and G where the composition is onto, but both F and G fail to be onto. I tried to make G not be onto, and when I did, that resulted in G composed with F not being onto. So it may be the case that in order for G composed with F to be onto, G has to be onto. We'll see. But the way we have the diagram drawn here, G composed with F is onto, but F is not. So we've answered this question in part. If G composed with F is onto, F does not have to be onto. So let's write that down. Oh, let me make sure I said that right. If F and G are such that the composition is onto, then F need not be onto. Okay, that much we've established. It looks like G does have to be onto, and that's what we're going to prove next. Here we go. If F and G are such that G composed with F is onto, then G must be onto. Now I'll note what our hypothesis is. And here we go, proof. Let the hypotheses be given. I won't write them out here. It'll just take too long and too much space. But here's what we want to show. Here's the conclusion. The function g from y to z must be onto. And we're going to show this in the conventional method. We're going to pick an element little z in set z and show that it has to be assigned to some element in set y by the function g. Now, what I'd like to do is go backward from set z to set y and show that there's an element y that is assigned to the element z by the function g. Unfortunately, nothing allows me to do that. What my hypothesis does allow me to do is go from set z, where I have little z in set z, and I can go back to set x, and there's an element little x in set x, such that z gets assigned to x by the function g composed with f. That's what my hypothesis allows me to do. So let's just go with the hypothesis. I think I'll give it a name. There exists an x and z. We'll call it x of z. Where x equals x of z, such that g composed with f of x of z equals z. Now, I think I'm more comfortable with a different form of notation. So I'll write it this way. G composed with f evaluated at x of z equals z. Okay. And now I guess the question is, where is this thing? F evaluated at x of z. Isn't this an element of y? Because f is a function from x to y, so wouldn't f of x be in y? So I'll just note parenthetically, G of f of x of z is the same as G evaluated at y, where y is f of c. Okay. Technically, I'm done right here. I've shown that the function G is onto. Let me just alert my listener to what, or my reader rather, what we just did. So given a z in set C, there exists a y in set Y, namely y equals f of x of z, such that g of y equals z. Hence, g from y to z is onto. In the next lecture, we will talk about the identity function. We'll talk about inverses and the relationship between inverses and one-to-one and onto functions.